Good morning. This is the second lectures of analog electronics for third sem electrical engineering. The topic is introduction and structure of semiconductor physics. Now we take the second topics or second lectures on the semiconductor physics. First of all, we discuss about the extrinsic semiconductor or doping process. What is the doping process and what is the extrinsic semiconductor? The electron or holes concentration can be greatly increased by adding the control amount of certain impurities. It means that the electron or hole concentration in any semiconductor can be increased by adding control amount of certain impurities. That process is called as the doping. Doping means adding the impurities to the semiconductor materials. This is the doping. For example, silicon, it is desirable to use impurities from the group of third and fifth. For silicon, we want to doping in silicon, so it is desirable to use the impurities from group third and fifth impurities as doping for the silicon. And N-type semiconductor can be created by adding phosphorus or arsenic. If we want to make a N-type semiconductor, so we should be doping or adding phosphorus or arsenic impurities into the semiconductor, silicon semiconductor. So after doping, this materials will be N-type semiconductor, or we can also doping pentavalent impurities to the silicon. The phosphorus is the group fifth atom is called donor impurities because it donates an electron that is free electron. So we know that some impurities are donor and some impurities are acceptor. Donor impurities donate an electron that is free to move, and acceptor impurities, that is the accept a free electron. The boron, that is the group third elements, has accepted valence electron. This is the acceptor silicons or acceptor semiconductor donate a hole. It is therefore can acceptor impurities. Okay. So group third elements are acceptor and group fifth elements behave as a donor. So these are the acceptor impurities and donor impurities which are used to doping to the semiconductor materials. You see in this slides, there is two-dimensional representation of a silicon lattice doped with a phosphorus atoms. In this dimension representation, a silicon lattice doping by the phosphorus atoms, because the phosphorus is the pentavalent impurity. So it creates a free electrons for the donor. Next is the p-type semiconductor. Also we know that there are two types semiconductor, or we can say that we classified the semiconductor in two types, p-type semiconductor and n-type semiconductor. Now we see in this slide, there is a two-dimensional representation of a silicon lattice doped with boron atoms. Here, the third group elements are doped to the silicon. So after doping the third elements, group elements to the silicon, so silicon will be behave as a p-type semiconductor. For example, the boron is the trivalent or group third elements. So after this doping of boron to the semiconductor behave as a p-type semiconductor, and doping of the phosphorus, that is the pentavalent element of fifth group. After doping to the semiconductor behave as a n-type semiconductor. So these are the two type semiconductor, p-type semiconductor or n-type semiconductor. Next, now we take the semiconductor device just as p-n junction diode. p-n junction diode is the simple electronics device that is formed by the p-type semiconductor and n-type semiconductor. After formation of p-type and n-type, there is a form a p-n junction diode. Diode is the simple two-terminal device, and which terminals are anode and second one is the cathode. Anode is the positive terminal and cathode behave as a negative terminal. And p-n junction diode, basically the application of this diode is for the rectification. What is the rectification? Rectification means convert the AC signal into the DC signal. So the main function of p-n junction diode or simple diode is the rectification. So you see in this slide here, there p-type material and here n-type material. In p-type materials, there are some holes and some electrons, and n-type material there are also some holes and some electrons. What in p-type materials, the number of holes are greater as number of electrons. What in n-type semiconductor or n-type material, the number of electrons is greater than as number of holes. So the in p-type materials, the holes behave as a majority charge carriers and electron behave as a minority charge carriers. But in n-type materials, the electrons behave as a majority charge carriers and holes are behave as a minority charge carriers. So this is the basic difference between p-type materials or n-type materials. The role of charge carriers is important in these two materials. In p-type materials, semiconductor materials doped with acceptors. Materials has high holes concentration because there is a number of holes are greater as compared to electrons. So the concentration of holes is high as compared to electrons. The concentration of free electron in p-type material is very low because there is number of electron is very low. So the concentration of free electrons in p-type material is very low. What we discuss about the n-type material, this is the opposite as a p-type material. There is a number of electrons are high, it means there is concentration of electron is much higher as compared to holes. In n-type materials, the number of holes is very low, so the concentration of holes is very low. So the in n-type material, semiconductor materials dope with donor. Donor, we dope the donor impurities, for example, phosphorus, arsenic. And example of acceptors impurities as a boron. This is the basic difference between n-type material and p-type material. Depend on the concentration of charge carriers, what is the concentration of holes, what is the concentration of electrons, which concentration is greater than, which concentration is low, which is concentration is high. This is depend on the type of material. In p-type material, you see here, in p-type material contains negatively charged acceptors immobile and positively charged holes free. The total charge is 0 because number of electrons recombine with number of holes. So total charge will be 0. In n-type material contains positively charged donors, that is immobile, in negative charge free electrons, so the total charge will be 0. Here a substance, the purple dots in solution, a membranes prevents movement of the water and the molecules from crossing from one side to breaker to the other. This is the in figure first. What in second, now that the gates have been opened, the random movement of molecules have caused over time the number of molecules to be equal on the two sides of the barriers. This is the phenomena of the charge carriers movement in a semiconductor device. We can explain here by the example of a substance of semiconductor materials. You see here, as a result of diffusion, the molecules or other free particles distribute ununiformly over the entire volume. Here is the diffusion of air, like the exchange of molecules from outside to the house to inside the house through the window. This is the phenomena of diffusion of electrons and holes, charge carriers movement process from one side to another side or into the semiconductor materials. Now, if what happened in PN junction diode, if n-type and p-type materials are in close contact, you see in this slide here, one side in left side is p-type semiconductor and right side is the n-type semiconductor. Both semiconductor are joined to each other. After joined to each other, there is a formation of junction. Junction is the joint part of the both semiconductor. Being free particles, electrons start diffusing from n-type material into p-type material. There are joint of two type materials, n-type materials and p-type material. So the free electrons or free particles electrons start diffusing from n-type material to p-type material. Being free particles, holes to start diffusing from p-type material into n-type material. Have they been neutral particles? Eventually, all the free electrons and holes had uniformly distributed over the entire compound crystal. However, every electron transfer a negative charge minus q onto the p side. P side means in p-type semiconductor, and also leave the uncompensated plus q charge of the donor on the n side. N side means the n-type semiconductor side. Every holes create one positive charge q on the n side and minus q on the p side. This is the process of generation of charge carriers. Every holes create one positive charge q on the n side and minus q charge to the p side. Now we see here in left side there is a p-type semiconductor and right side is the n-type semiconductor, and is a junction between mid center of two semiconductors where they are joined to each other. So there will be in p side across the junction there will be some negative charge carriers deposit in the p side, and some positive charge are deposited in the n side of the across the junction. Across the junction, the charge are deposited and these charge are immobile. So this immobile charge layer is called as the depletion layer. That depletion layer form across the junction, and there is the immobile charge carriers. In p side, the negative charge carriers, and n side, the positive charge carriers. So the electrons and holes stay close to the p-n junction because negative and positive charge attract each other, because we know that the positive charge and negative charge both are attracted to each other. What the positive charge or negative charge are repulsion to each other. But here the charge is opposite, positive and negative, so that there is a attraction to each other. Negative charge stop electrons from further diffusion, and positive charge stop holes from further diffusion. This is the process across the junction. Negative charge stop electrons from further diffusion, and positive charge stop holes from further diffusion. The diffusion form a dipole charge layer aid the p-n junction interference or p-n junction. There is a built-in voltage at the p-n junction interface that prevents penetration of electron into p side and holes into the n side. So there is the voltage interference junction across the junction that is prevent the penetration of electron into the p side and holes into the n side, because in n side the holes is minority carriers, and what in p side the electrons are the minority carriers and holes are majority carriers, and n-side electrons are majority carriers. Now the polarity shown attract holes to the left and electrons to the right. Now we form a PN diode which have the two terminal, positive terminal and negative terminal. Positive terminal is the anode and a negative terminal is the cathode. So this formation is form a PN junction diode which have the two terminal, positive terminal and negative terminal, or anode terminal and cathode terminal. According to the current continuity law, the current can only flow if all the charged particles move, forming a closed loop. This is the current continuity law for the flowing the charge carriers. However, there are very few holes in n-type materials and there are very few electrons in the p-type materials. So there are very few carriers available to support the current through the junction plane. For the voltage polarity shown, the current is nearly zero. So the polarity shown attract electron to left and holes to the right. There are plenty of electrons in n-type material and plenty of holes in the p-type materials. So there are a lot of carriers available to cross the junction. There are a lot of carriers cross the junction. So when the voltage applied is lower than the built-in voltage, so the current is still nearly zero. We applied the voltage, external voltage. So this voltage is lower than the built-in voltage, so the current is still nearly zero. When voltage exceed the built-in voltage, so current can flow through the PN junction. This is the condition for the applied voltage. What is the applied voltage is should be greater than or should be less than. If the applied voltage is greater than, then the current can flow through the PN junction. But in condition of if the applied voltage is lower than the built-in voltage, there is a current is zero or nearly zero because there is no movement of charge carriers across the junction. So the total current will be zero across the junction or no flow the current in the PN junction diode. This is the condition for the conduction of PN junction diode. It is depend on the applied voltage and built-in voltage. Now you see here the diode current I equal to, this is the diode current formula which flow in diode. So we can explain the diode current I equal to Is e to the power QV upon KT minus 1. So semiconductor diode consists of PN junction with two contact attached to the p-type and n-side. Here, what is the I and what is the Is? and what is the K and T. So here IS is the very small current, or the ideal value of the IS is the 10 to the power minus 17 to 10 to the power minus 13 ampere. This is the very small value of current. When the voltage V is negative or reverse polarity, so the exponential form or exponential term equal to -1, the diode current is equal to Is very small. This is the condition. When the voltage V is positive, this is the second condition. B is the negative, this is the first condition. Now we take the second condition, V is positive or forward polarity. The exponential term in the given equation increase rapidly with V, and current is very high. So the current is very high in that condition when the V is positive or forward polarity, and V is negative or reverse polarity, then diode current is very small, or the range of current is the 10 to the power minus 17 to 10 to the power minus 13 amperes. This is the also called as a reverse saturation current. Is is the reverse saturation current. The amount of reverse saturation current is very small as compared to diode current. The range of the diode current will be in milliampere. What the range of the reverse saturation current will be nanoampere or more, very less. Here the resistor Vi equal to IR, or we can find out current I equal to V upon R. So the Vi characteristics of a resistor we can draw here. The relation between current versus voltage. Here is a straight light. This is the relation between the voltage and current. This is also follow the Ohm's law. V equal to IR. Now we take the Vi characteristics of PN junction diode. So here we see that simple PN diode, we can apply voltage, external voltage to the PN junction diode. That voltage, external voltage, is called as a biasing voltage. The bias voltage can be divided into two types: forward biasing and reverse biasing, or we can say that the diode can be biased by forward biasing or reverse biasing. This is the two type of biasing of PN junction diode. So what is the forward biasing and what is the reverse biasing? In forward biasing, if the positive terminal of the diode is connected to the positive terminal of external battery, and the negative terminal of the diode connected to the negative terminal of external battery. So this process is called as the forward biasing. What in reverse biasing, this is the opposite. If the positive terminal of PN diode is connected to the reverse or negative terminal to the battery, and a negative terminal of the diode connected to the positive terminal of the battery, that is the reverse biasing process. What we know that the diode only conduct in the forward bias condition, not in reverse bias condition. So we draw the characteristics of PN junction diode or VI, current versus voltage graph. So you see here in this graph, the current, we increase the current, the voltage also increase with the current. So this is the, in first quadrature, first quadrant, this is the forward biasing condition or forward bias curve between the current and voltage. What in reverse bias condition, the diode is in off state, so there is no current flow. So the graph between current versus voltage in third quadrant, you see here, here is no, we increase the voltage but there is no increase current. So very small current flow in reverse bias condition. So this reverse bias condition current is also called the reverse saturation current, or the value of reverse saturation current is very small, or in the range of the nanoampere. What the, in forward bias condition, the value of current of diode in the range of milliampere. So this is the very big difference between forward bias current and reverse bias current. So you see here a diode current equation, I equal to Is e to the power QV upon Kt minus 1. Here Q is the electrons charge carriers, K is the Boltzmann constant, and T is the temperature of room temperature, and V is the applied voltage of the diode. That voltage may be external voltage. So this is the graph between current versus voltage of the PN junction diode. This graph also called as the PN junction diode characteristics graph. You also see in this graph here some voltage on x-axis. Here is some 0.5 voltage and 0.7 voltage. This is the cut-in voltage of PN junction diode. After cut-in voltage, the diode will start to conduct, and the current increase will increase the voltage. But up to the cut-in voltage, we increase the voltage, but there no increase the current. So cut-in voltage is that voltage of the PN junction diode, after which voltage the diode will be start to conduct or current increase, so also voltage increase. This is the forward bias condition, and this is the reverse bias condition. In reverse bias condition, we increase the voltage, but there is no increase current, or means no conduction of diode. So the current value is very small, in the range of nano amperes. What we increase the voltage and increase the voltage at a particular condition comes here, then current increase very sharply at a particular voltage. That voltage is breakdown voltage, and that current is the breakdown current. And this phenomena is also called as a breakdown phenomena, where the current rapidly increase or suddenly increase with the voltage. This is the breakdown phenomena which is occur in the reverse bias condition of PN junction diode. We can represent diode as a symbol by this here, simple a positive terminal and negative terminals. Positive terminals is anode and negative terminal is cathode. So this is the symbolic representation of PN junction diode. This is the circuit diagram of PN junction diode. Here is the PN junction diode and one is resistance, and here is the external applied voltage or biasing voltage across the PN junction. So when plus is applied to the P side, then current is high. So this voltage polarity is called forward. And then plus is applied to the N side. So current is nearly zero. This voltage polarity is called reverse. This is a reverse polarity and forward polarity in the PN junction diode. Now we see here in this, the PN junction can emit the light when forward bias. Or this is the example of PN junction diode is LED, light emitting diode. When electrons and holes are attract to each other, then energy generated, or that energy generated in the form of light, and this is the process in the light emitting diode, LED, light emitting diode. So this is the example of simple PN junction as a LED, light emitting diode. So electron drift into P material, and finally plenty of holes there. So they recombine by filling up the empty positive position. Holes drift into a material and find plenty of electrons there. They also recombine by filling up the empty position. This is the holes drift, and the energy released in the process of annihilation produce photons, particles of light. This is the phenomena which is occur in the light emitting diode. Here we see in this circuit diagram, here is the forward biasing condition for the PN junction, because the positive terminal of the diode connected to the positive terminal of battery, and the negative terminal of the diode connected to the negative terminal of the battery. This is the forward biasing condition for the PN junction. So you see here, if we applied the reverse external applied voltage to the this diagram, so we see here that here is the N-type material and left side is the P-type material. It means that in P-type materials there are number of holes are majority charge carriers, but there is electrons is very low charge carriers, that is the minority charge carriers. But in N side there is number of electrons are more as compared to holes. So the electrons here majority charge carriers and holes are negative holes are, sorry, positive charge carriers. So we applied the external applied voltage in forward bias condition. So we see here that the positive, here is the positive charge, and we connect the positive charge or negative charge of the battery terminal. So we see here that the P type, it means here is the majority P type charge carriers connect to the negative terminal of the battery. So there is a repulsion. So there is a attraction. So all positive charge are attracted with the negative terminal of the battery in P side. What in N side, there is majority electron charge carriers attract with the positive terminal of the battery. So there is attraction. So this is the process of the diode conduction, and in this process the movement of charge carriers across the junction and the current flow due to the recombination of charge carriers, holes and electrons to each other. So this is the process of the diode conduction process. Now we come on the what is the application of the PN junction diode. PN junction diode simply used as a rectification purpose. Rectification means convert the AC signal into DC signal. The best example of mobile charge that convert the AC signal to the DC signal for a particular rating of the DC voltage, because we know that the input supply voltage of AC signal is 220 or 240 voltage, but the mobile charge only 5 volt or 9 volt DC supply. So first of all, we convert the AC supply into DC supply to a particular rating voltage. So for this purpose, the conversion of AC signal to DC signal, we form a bridge circuit with the help of diode. There is 4 diode generally used to formation of mobile charger, and one component, some components, one is resistor, second is capacitor, and one is the transformer. So these are the some components of mobile chargers: transformer, diodes, number of diodes, numbers of capacitor, number of resistor, and we form a circuit diagram with the help of these transformer, diode, capacitor, and resistor, and we easily convert with the help of diode circuit the AC signal into DC signal. So this is the very important role of PN junction diode in the conversion of rectification. So this is the main application of PN junction diode. Also diode we have, or we can use as a switching device. Diode as a switching device, because diode we have as a switch, because diode conduct only in forward biasing condition and not conduct in reverse biasing condition. So the diode conduct in forward bias behave as a on condition, and what in reverse condition diode is off, so switch behave as a off. So we can use as a PN junction diode as a switching device, or switching means on off on off behave as a switching. In on condition the current is flow and diode is conduct. What in reverse bias condition diode is off and there is no flow of current, so we have as a off condition, so the diode we have as a switching device. So diode we have as a switching device, diode we have as a rectification device. These are the mainly application of diode, which is the very important role in electronics field of the diode. And now these are the some books which is to cover the this lectures. First is the electronics, author is Millman and Halkias. Second books is electronics device and circuit, which author is Bolested. These are the very useful books to cover the this topics. And some are multi-choice questions of this topics, so you can attempt and solve these questions, and after solving these questions you can easily understand the concept of semiconductor materials and semiconductor device. And this is very beneficial questions for the this topic, so please you attend these questions. And thank you very much.